guys, welcome back to the LearnAPChem series here at LearnAP. In this video we're going to cover Lewis structures, molecular geometry in VSEPR, sigma and pi bonds, and hybridization or hybrid orbitals. Before we get going, leave a comment if you're confused or have questions, or you can also ask in the weekly live streams we do from 5 to 6 p.m. Eastern every Sunday, where we answer your questions about AP chemistry. Other than that, let's get started. Alright, so let's start by talking about Lewis dot structures, or just simply Lewis structures. And these are representations of an atom or a compound's electrons. So we can write Lewis structures for an atom or like a compound like water. To draw a Lewis structure for an atom, write its symbol and then put a dot for each valence electron around it. So here for carbon, we're just going to write its symbol, just C, and then the number of valence electrons. Now I know off the top of my head carbon has 4, but you could look at the periodic table if you didn't know. Now to draw a Lewis structure for a compound, write the Lewis structure for each atom side by side. Now after that you're going to draw bonds with a bar until each atom has an octet. Now note that one bar between two atoms represents a single bond, 2 a double bond, etc. So here for water we're going to start by writing the Lewis structure for each atom side by side. So I'll just get some space here. So we have oxygen, which I know has 6 valence electrons, and hydrogen each has 1. But hydrogen's a little funny, it doesn't want an octet, it only needs 2. So here we can see that oxygen is short 2, we need 2 here, and hydrogen, both of them are short 1. So I can draw bonds between these two and fill their octets. So for each bond I'm just going to erase an electron and draw a bar. And now we can count the octets. So here, if you see a bond to an atom, you count it as 2. So here there's a bond to hydrogen, we have 2, we have a full octet, same here. For oxygen, we have 1, 2, 3, 4, and then a bond, 5, 6, 7, 8. So we have a full octet. Now there's a problem with this Lewis structure though, is you never draw a bond in dots sort of on the same side. So like, if we have a symbol, we can put electrons here, 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 and here. But you would never sort of draw it like this, where you have a bond going to one side as well as an electron. So all I have to do is just erase these two and write them up here. Alright, just another quick note, if your Lewis structure has a net charge, write brackets around it and then write the charge outside of the brackets. So let's say that I had F minus. I know that F minus has a full octet. Fluorine normally has 7, but I have an extra electron. And this is how I would draw it. I'd put the brackets around F and then put the negative sign to indicate the -1 charge. Alright, now let's move on to VSEPR theory and molecular geometry. Now VSEPR is an abbreviation for this short, sort of long thing called Valence Shell Electron Pair Repulsion theory. Now that sounds really complicated, but all it's saying basically is that electron pairs are going to repel each other. And because of that, we can determine the molecular geometry, or 3D shape, of covalently bonded molecules. Now the region in space occupied by bonding electron pair, or pairs, is called the bonding domain. So if I'm dealing with H2O, let's quick draw the Lewis structure. This here would be what's called a bonding domain. It's occupied by a bonding electron pair. Now the region in space occupied by a non-bonding electron pair or pairs is called the non-bonding domain. So here would be the non-bonding domain. because these electrons here on oxygen are not participating in the covalent bond. So that's all VSEPR theory is. Basically, because electrons repel each other, we can use that to determine the sort of shape of the bonds of a compound. Alright, so let's talk about some basic molecular geometry structures. Now each has its own notation. The shape name, I've included like an example molecule, and then the angle that the bonds make with each other. So how do you determine, like say H2O, how would I determine what shape it is? Well, what you would have to do is you're going to have to write the Lewis structure. We've done this already, so pretty straightforward. And then you're going to count the number of bonds. So here I have 1, here's 2, so I have 2 bonds. Now note that if I had like a double bond, this would only count as 1. So here we have 2 bonds. And then count the number of lone electron pairs. So here for water we have 2, 1 here and 1 here. So 2 electron pairs. And then you're going to think through which shape matches that description. I've included a link in the description with a full table. So you would memorize that and you would think back to that table, okay, which shape has 2 bonds and 2 electron pairs? And then you would say what it is, and then you can correspondingly find like the angle. So that's how you use this. Again, I've included a link in the description for the full table, and you should definitely memorize that as soon as possible. Alright, now let's talk about hybridization. Now when an atom bonds, sometimes its orbitals undergo hybridization. Now the hybrid orbitals you need to know are sp, sp2, and sp3. You might have heard of sp3d or sp3d2. These are not going to be on the AP chemistry test. There's sort of a debate as to whether they actually exist. So they are not on the AP chemistry test. You don't have to worry about those. Just know sp, sp2, sp3. Now, to determine how an atom will hybridize, think about how many lone pairs and bonds an atom has. So for example, CH4, I'll just quick draw the Lewis structure because I know it. Now here we look, we have 4 bonds and 0 lone pairs. So we need to essentially hybridize 4 orbitals. And so carbon is going to hybridize sp3. You can also know the hybridization just from knowing the molecular geometry and the corresponding hybridization of that molecular geometry. But if you don't know that, you can just sort of think about how many lone pairs do I have, how many bonds do I have, so how many orbitals do I need to hybridize? In this case it's 4, so we have sp3. So 1 for the s, 3 for the p. That's 4. Hybridization relates to molecular geometry, as I was saying, in that certain structures hybridize in certain ways. And this information will be in the chart in the link in the description I talked about earlier. So memorize the molecular geometries and also memorize the corresponding hybridizations of each. Alright, so that brings me to today's challenge problem. How many sigma and pi bonds does NO3- have? What is its hybridization? What is its molecular geometry? So the solution to this is on our website, learn-ap.com. I'll also include a direct link in the description. If you guys found this video helpful, please like and be sure to subscribe for future content. Like us on Facebook and follow us on Twitter for updates about our new videos and live streams, which we do every Sunday, 5 to 6 p.m. Eastern, where we answer your questions about AP Chem. Links for that will also be in the description. Leave a comment if you're still confused on any of this stuff, or also any other comments on the video in general. Other than that, I want to thank you guys for watching, and I'll see you in the next video.